This video is to take a look at how we determine the key features of sine equations. Before we continue with this video, we just want to do a quick review of what the key features we would even be looking for would be. The example on the screen is an example of a periodic function. There are a number of things that we can be looking for periodic functions, so we'll just quickly review them. The first thing that we'll be talking about with a periodic function is its midline. The midline is the middle height of our function. So if I were to take a line and put it approximately here, it would be halfway between the highest and the lowest height of our graph. So this line right here, which I would say is y equals 2, would be an example of our midline. The next idea that we could talk about would be something that we call amplitude. Amplitude is only really defined in relationship to the midline. So if I take a look at my midline, I see how far it is from the middle to the top. So that's from the midline to the maximum, or from the midline to the minimum. That distance is what we call amplitude. So it's kind of the building block, with the foundation being the midline. In this example, 5 minus 2, 5 of the max, minus the 2 of the midline is 3, and our amplitude is 3. Additionally, we can talk about how often our function is repeating, so how long it takes for one of the patterns to repeat, the pattern to start to repeat itself. So if I start at my midline here, and I travel along my curve until I get to the next spot where the pattern would start to repeat, so right around here. That's the end of what we call one cycle. How wide that cycle is what we call period. So this distance from here all the way back to where the cycle started is what we call one period. So this is one cycle. And the width of the cycle is what we call period. So when I look at this graph, I see that the period ends at 4 pi and it starts at 0 pi. So in this particular example, the period of the graph is 4 pi. Now, in order to graph a periodic function, we first need to determine all of these key features of my graph, so be able to determine the amplitude, the period, the midline, etc. And then additionally, we'll also be able to tell these labels along the x-axis. The question becomes, how do I tell that? And it all comes from the placement of additional numbers into the equation of my function. We've already done a decent exploration looking at what the a value, a number in front of sine or cosine functions, does to it. And we saw in those explorations that the a value gave us kind of a vertical change. So our maxes and our minimums changed. So we saw that if the absolute value of a was bigger than 1, then our graph had what we called a vertical stretch. If the absolute value of a was between 0 and 1, then we had a vertical shrink or a compression. Some people call it a compression. We'll probably call it a shrink most of the time. The other important is that if a is negative, regardless of its value, if it's less than 0, then it takes our graph and it reflects it, flips it upside down, so it reflects it over the x-axis. So what that means is that maximums, things that used to be maximum heights, are going to become minimum heights and vice versa. So because it gives me a vertical stretch, we think back to our previous graph where the maxes and mins are, it comes from the idea of amplitude. So it actually winds up that the a value, absolute value of it, I don't care if it's negative or positive, whatever that a number is equivalent to the amplitude of our graph. Sorry for the squeaking there. So that's what A does. I want to hold off on B because B is a little bit more confusing. I'm going to move on to the other two that I'm pretty sure we're more comfortable with. And I'm going to go to, I guess I'm going to go to C next. If I put a number inside, adding or subtracting from the x, that's going to impact left or rightness of our graph. So if in my equation I see, pardon me, if I see x minus c, that implies that c is positive based off of the general form, and that implies that I am being moved or translated right c units. And if I see x plus c for my equation, that's implying that the c value is negative because the standard form has the negative built in right there. So this is opposite of what we're doing. So that would mean that I was moving left c units. In terms of what does this impact, well, the only thing I guess it really impacts is kind of our starting point. So this is going to give us the x value of our starting point. D is the next one that we're comfortable with. We used it with all of the other functions that we work with so far. If I have a number added or subtracted to the end of my function, we know that that gives us an up or down translation. So if I have plus D, that means that my graph is getting moved up D units. And if I have minus D, it means that my graph is getting moved down D units. Now, if I think about taking my graph and actually sliding it up or down, my maxes will change, my minimums will change, but the relationship to that middle height will remain the same, which is not true about amplitude. So what that means is that the midline of my graph is always the D value, right? It used to be at 0 for the parent function. Once I move it up or down, it will move to that new height. So the midline equation will always be y equals whatever the D is. And the last thing that we can talk about is B. Like I said, we had not really discussed B in past years. This is new to the periodic function concept. We could talk about with other functions, but there's been no reason to. So when I have a B value, what it does is it takes my function and it stretches or compresses it horizontally. So we can say if the absolute value of B is greater than 1, what's happening is the frequency of my graph is increasing. It's saying it's moving at a higher speed. So if it's bigger than 1, that we're going to say that we have a horizontal. This is backwards because it's speeding up. So this is going to make my period smaller. So it has a horizontal shrink. Because it's getting smaller, I don't want to say by B. I want to say it's by the reciprocal of B. So I'm going to write 1 over because we know that 1 over something means reciprocal of. And if my B value is between 0 and 1, then we're going to say that we have a horizontal stretch by, again, the reciprocal of B. So if the B value is a half, then it's being stretched by a factor of 2. It's moving half the speed, so it's taking twice as long to get through one cycle. So here's what that means. It means two things. One, it means that my frequency of my graph, how often it occurs, can always be found by taking the B value and putting it over 2 pi. It says how many times, how many cycles do I get in within 2 pi radians? And more importantly, it means that the period of our graph equals 2 pi divided by B. I want that to look even clearer because this is the big key point of the B value. So we're going to say period equals 2 pi over b. And like I said, that is like the key graphing component there. Without being able to determine the period, I can't really start to graph at all. So those are the key features. What they tell us in terms of our key elements, max, mid, amplitude, etc. And then how we would describe them using general function transformation terminology that we've seen in previous years. I guess the last thing that I should add now that I'm just looking at this is that if I have my amplitude and my midline, if I put the two of those things together, I can figure out the maximum and minimum heights of my function. So because that's the building of the amplitude off the midline, so the maximum value will always be the midline d value plus the absolute value of a, so plus the amplitude, and the minimum will also therefore be the midline value minus the amplitude of our graph.